Hi, welcome back. In this video, we're going to talk about how to factor polynomials of degree 4 to the fourth power. Now, we're going to be using the rational root theorem that I did in the previous video. So, if you do not know the rational root theorem, look at part 1 because part 1 focuses on cubics, right? It's good to know how to do the rational root theorem first, and then how can I apply more things to the rational root theorem later. Right? So only watch this video if you're feeling comfortable with doing the rational root theorem for cubics. Okay? I'm going to be showing you two examples today of polynomials to the fourth power. And after today, you can use this video or this set of instructions to do anything beyond. So to the fifth, to the sixth, or even higher. We're only going to go to the fourth power for this class. But this technique that I'm going to show you can be applied for anything higher of degree fourth. All right, let's get to it. Let's do two examples here today, and let's see how we feel about it. If you haven't subscribed, this would be a perfect opportunity for you to do that or to share it with your grandma so that she can subscribe to my channel. Just kidding. Unless your grandma's into math, then of course, you know. All right, let's talk about to the fourth power. So, like in the previous video, we're going to be focusing on the leading coefficient. We're going to call this one Q. And then the constant, which is the last number with no variable, this is going to be called P. Our goal first is to start by looking at the possible factors, right? What are the factors of P and Q? So I'm going to look at P first. The factors of P, I can multiply 1 times 12, right? 1 times negative 1 times 12. I can multiply 2 times 3, 2 times 6, 3 times 4. I have all of these different factors that I can use. So I'm going to focus on the positive and negative version of 1 times 12. I'll do 12 here, right? I could do 1 times 12 or 1 times negative 12 or negative 1 times 12. I can look at positive minus 2 times 6. As long as one of those is negative, I can get a 12. So negative 2 times 6 or 2 times negative 6. I can also multiply 3 times 4, so plus or minus 3, plus or minus 4. These are all the possible factors of 12. There's a lot of them here, right? There's 2, 4, 6, 8, 10. There's 12 different factors that I can get. Now, for the leading coefficient, thankfully we have a positive 1. So the possible factors of 1 are positive 1 times positive 1 or negative 1 times negative 1. After you find the possible factors of, we're going to find the combinations, right? What are the combinations? Of P over Q. Remember, our goal here is to create a rational number. A rational number is a fraction. A number that can be expressed as a fraction. And here, when I start to divide P over Q, all the different combinations, I'm going to have a ton of different fractions. And since there's 1, 2, 3, 4, 5, 6, since there's 6 times 2, there's 12 different numbers on top, and there's 2 in the bottom. 12 times 2, there's actually going to be 24 different fractions that I can have when I'm combining all of these numbers. We're not going to need 24. We really only need about half of that to find our solutions. So let's start with some of these, right? Let's say we're dealing with positive 1. If 1 is a possibility, I can divide it by positive 1, or I can divide it by negative 1. Right? If negative 1 is a numerator, I can divide it by 1, and I can divide it by negative 1. And I can go through this list for all of them. I'm going to start with the smaller numbers, like 1, 2, maybe 3. I don't have to do all of these. That's too many numbers. Let's start with 2. If 2 is a numerator, then I can have positive 1 as a denominator, or I can have negative 1 as a denominator. If negative 2 is a numerator, I can divide it by 1 or by negative 1. I can go with 3 as well. 3 or negative 3. I can divide 3 by positive 1 or negative 1. I can also divide negative 3 by 1 and negative 1. This is enough to find the possible roots that I'm looking for. I don't have to go through all of these. You're welcome to find all of the 24 different fractions that are possible. That's not necessary at all. Now here, the possible combinations are 1, 2, 3, 4 times 3. This is 12 different combinations, which can be simplified to a lot less unique values, right? 1 divided by 1 is 1. I can get a 1 like this. I can also get a 1 when I'm dividing both negatives. I can divide 1 divided by negative 1 is negative 1. I can get a negative 1 here and here. I can get a positive 2 here and here. I can get a negative 2 when when only one of them is negative. I can get a 3 here and here. And I can get a negative 3 here. I do not want to go beyond 6 different intercepts, right? Now, in these 6, at least one of them will be an x-intercept for my to the 4th power problem, for my polynomial. I don't need to go through all 24 to figure that out. So then this is where we went, right? We are first trying to find the unique x-intercepts that can be possible. And we have to test this out using our synthetic division. So we're going to go and start with our synthetic division problem. We start with a 1 as a coefficient, negative 4, negative 1, 16, negative 12. And we want to know, does 1 fit into this polynomial? I'll move it over. Is 1 a solution? So let's see if it factors out nicely. When you bring down the 1, you multiply. 1 times 1 is 1. When you add these, you get negative 3. 1 times negative 3 is negative 3. You add those, you get negative 4. 1 times negative 4 is negative 4. As you add these, you get 12. 1 times 12 is 12. And when you add these, you get 0. That worked out in our first attempt. So x equals 1 is a solution. What does that mean? It means that we can now write this as a factor, right? If x equals 1, as a solution form, the factored form, we would move the 1 back, and we would write the factored form as x minus 1. Right? This is the factored form of the solution. Now, since we started with to the 4th power, if we're dividing it by a single x value, we should have x cubed left over. So that's the meaning of this, of these coefficients. That means that we're going to have 1x cubed minus 3x squared minus 4x plus 12. Yeah, I have one factor and then I have my cubic. Now the thing that's different for this part of the unit, or for these types of problems, is that now how do we factor this cubic? Well, I would have to repeat the previous steps. We factored cubics in our previous video using the rational root theorem. So we can actually start this process again. We could look at the possible P and Qs that result in this process. I would look at, let me see, I would look at P here, Q here. I would find plus or minus 1, plus or minus 2, plus or minus, since we're dealing with the same number, the 12, right? We basically have the same values that we're using over here. Plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. We're going to have the same combinations. And since 1 is the same in the front, we're also going to be dividing it by plus or minus 1, just like we did here. So all of them are going to come down to the same thing. If I do this again for the new one, which is a cubic, I will now have unique P and Q values of 1, negative 1, 2, negative 2, 3, negative 3, dot, 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 dot. I would repeat this process again, but since they're the same numbers, I can tell that they're going to be the same ones as before. So let's try something else. We've already tried x minus 1. Let's try to see if 1 fits into this polynomial. Now we're going to be focusing on factoring this cubic, knowing that x minus 1 is already part of my solution. Somewhere in the answer choice, x minus 1 will be part of it. Now I need to break down the cubic again, right? So let's try 1 out. Does 1 fit into this cubic? 1, negative 3, negative 4, and 12. Let's bring down. 1 times 1 is 1. When I add those, I get negative 2. 1 times negative 2 is negative 2. When I add these, I get negative 6. 1 times negative 6 is negative 6. This does not add to 0. So 1 is not a x-intercept. Let's try negative 1. This is a trial and error portion, right? I got to try them all out until something works. Negative 1 times 1 is negative 1. As I add these, I get negative 4. Negative 1 times negative 4 is positive 4. Right? When I add these, I get 0. Negative 1 times 0 is 0. When I add those, I get 12. I do not get 0 as a remainder. Try the next one. Let's try 2 out. 1, negative 3, negative 4, and 12. 2 times 1 is 2. When I add those, I get negative 1. 2 times negative 1 is negative 2. When I add those, I get negative 6. 2 times negative 6 is negative 12. This adds up to 0. We did it. We found the next x-intercept. X equals 2 worked. So we know x minus 1 is a previous factor, which means this one came from what factor? If I move the 2 back, this one came from x minus 2. I have 2 factors already. What is my resulting polynomial? Well, this one was a cubic. Cubic divided by a single term results in a quadratic. So that means that this is a quadratic. I have 2 linear. Now I have a quadratic. Can I factor the quadratic? The factors here are going to be x times x is 1x squared, and 3 times 2. As I cross multiply, I get 3x and 2x. In order to get a negative 1, I have to do 2 minus 3. So I have my factors here. X minus 3 and x plus 2. So since it's to the 4th power, I'm dealing with 4 factors, right? F of x equals x minus 1 times x minus 2 times x plus 2 times x minus 3. Here's my factored form up to the 4th power. All I did is I repeated the rational root theorem twice. I did it to find the cubic, and then I did it again to the cubic to find the quadratic, so that I can find my 1, 2, 3, 4 factors. Now, there's actually a faster way for this particular problem. This is how I would approach any general scenario that's dealing to the 4th, to the 5th, or higher powers. But here's what I want to show you real quick. Notice how here, when I repeated the previous steps, I could have done a different approach. Here's what I'm going to do. I'm going to try a slightly different approach. Since I'm factoring a cubic, you can factor all cubics using the rational root theorem, which we did. But notice how this cubic can also be done through grouping. If I factor out an x squared from both of these terms, I'm left with x minus 3, right? If you divide that by x squared and that by x squared, you're going to be left with x squared times x minus 3. What do these two share in common? Well, they're both divisible by negative 4. And if I divide both by negative 4, that results in positive x minus 3. What do these two groups share in common? An x minus 3. So if I divide both by x minus 3, I'm left with x squared minus 4. So I have my original factor, x minus 1, which came from the previous problem, which we had to do using the rational root theorem. There's no way around that. We had the x minus 3, and then I can break this into two more factors, right? We have the difference between perfect squares. This turns into x minus 2, x plus 2. I have the same four factors as we did over here, except that here I use grouping when I had the cubic. And over here, I did the rational root theorem when I got my cubic. They both result, as you can see, with the same four factors. So if you can use other methods other than just rational root theorem, I recommend that. Yeah, I know that looks like this is a lot, but this is why it's important that for you to know the rational root theorem from the previous video. So if you're not feeling comfortable with doing to the third power, like how to do this kind of a problem, doing multiple steps for the same scenario would be too much. Let's try another one to simplify this thought process for us, yeah? Let's try one more. All right, here's P. In front, we have Q. We start by looking at the factors of P and Q. Factors of P and Q. For P, what do we got? To get 9, you can multiply 1 times 9 or 3 times 3. So plus or minus 1, plus or minus 9, plus or minus 3. To get 1, we have plus or minus 1 for Q in the bottom. Right. Now we're going to look at the possible combinations here. There's going to be a lot of possible combinations. In the top, we have 2, 4, 6. We have 6 numbers on top. We have 2 numbers in the bottom. So 6 times 2 is 12 possible combinations. It's important to look at all the possible combinations because we're trying to find the rational numbers that will be a root. Yeah, so if 1 is positive on top, I can divide it by 1, or I can divide it by negative 1. If on top we have a negative 1, I can divide it by 1 or negative 1. Now let's look at 3. If the 3 is positive, I can divide it by 1 or negative 1, and if the 3 is negative, I can divide it by 1 and negative 1. I can do the same thing with the 9. If I have a 9, I can divide it by 1 or negative 1. If I have a negative 9, I can divide it by 1 or negative 1. I have found a total of 12 different combinations here. How many of them are unique? Well, let's look at the unique P over Q's that we have. Yeah. 1 divided by 1 is 1. That happens here and here. If I divide by a negative 1, I can have a negative 1. That happens here and here. If I divide 3 over 1, I can have a positive 3 here or here. I can divide by a negative 1, which results in a negative 3 here and here. I can have positive 9 and negative 9 here and here. So I have 6 possible x-intercepts from all of this. Let's start by plugging the 1, right? We always start with the smallest values. You can go in whatever order you want. I'm going to start with the smaller numbers and eventually get to the 9s. So let's test out if 1 is a factor. Let's see. I have 1, negative 6, 8, 6, and negative 9. This is my original problem, right? Let's test it out. 1 times 1 is 1. Add them up, you get negative 5. 1 times negative 5, you get negative 5. When you add these, you get 3. 1 times 3 is 3. When you add these, you get 9. 1 times 9 is 9. That gives me a 0. That worked. I didn't have to go through all of them to make it work. You could technically test out -1, 3, -3. You can do this over and over again to find all the x-intercepts, if you like. Or we can convert this into factored form, right? Since x equals 1, the factored form of that was x minus 1. Right? You move the 1 over to the left. When you move it over, you get x minus 1 equals 0. So my factored form is x minus 1. Here, since I'm dividing a to the 4th power over a single x solution, x to the 4th divided by x results in x cubed, which means the remaining piece is a cubic. 1x cubed minus 5x squared plus 3x squared plus 3x plus 9. These are my two, right? X times x cubed is x to the 4th. Now we can still factor the cubic. What can I do here? Well, you can treat this as p and as q and repeat the process. Repeat rational root theorem. Or, is there another way to factor this cubic? Sometimes it's possible to do it through grouping. Is it possible to do it through grouping? Let's test it out. Let's see, what do these have in common? They have an x squared in common. If I divide both by x squared, what do we have? This is x minus 5. Here, what do they both have in common? A 3. If I divide both by 3, I get, what, x plus 3. But notice how both groups don't have anything in common. So I wouldn't want to do this one using grouping. Grouping does not work. All right, well, we can always go back and use the rational root theorem for this one, right? So let's use the rational root theorem. I'm going to repeat the process for this problem using the rational root theorem. I already have x minus 1 as one of my factors. Let's do it for 1x cubed minus 5x squared plus 3x plus 9. This is p. This is q. What are my factors going to be? Well, plus or minus 1, right? Plus or minus 3, plus or minus 9. And then divided by 1. To get 1, I get plus or minus 1. Here, when I start to divide, I'm going to end up looking at some of the same ones, right? I just need to have a handful of these to test out. So what are the unique values, right? What are the combinations? Combinations of p over q. Let's see. I can do 1 over 1, 1 over -1, -1 over 1, -1 over -1. I can do things with 3's and -3's. I have 1, -1, 1, -1. I can do, I don't need to go further. I don't have to go all the way to 9. I just want to test out a few of these, right? So p over q. What are the unique p over q's? 1 over 1 is 1. I can have it here and here. This gives me -1, which happens here and here. I can test out a 3 here and here, and a -3. This should be enough to find something, right? I don't have to go all the way through the 9's and all the other scenarios. Let's test out 1. Remember, we already have a factor. For the solution, we already have one of them. This one's already there. We're trying to find the other ones for this cubic. So let's test it out. We're trying to plug in the 1. Let's see if 1 works. Our coefficients are 1, -5, 3, and 9. 1 times 1 is 1. When you add those, you get -4. 1 times -4 is -4. When you add those, you get -1. 1 times -1 is -1. This does not give you 0 as a remainder. So that's not a solution. Let's try -1. -1 times 1 is -1. When I add these, you get -6. Negative times a negative is a positive. When I add these, you get 9. -1 times 9 is -9, and that gives me 0. I found my solution. This one will be a solution. So if x equals -1, what was the factored form? We'll bring the 1 back. The factored form was x plus 1. That's what that represents. How do I interpret the rest? Well, we had a cubic. Cubic divided by a single term, right here, results as a quadratic. So that means that this is a quadratic. And now the question is this factorable? I already have a factor here as x plus 1. So I have x minus 1 and I have x plus 1. Can I factor this quadratic further? 1x squared minus 6x plus 9. Well, let's factor this. X times x, and here I have 3 times 3. When I cross multiply, I get 3x and 3x. The only way to get a -6 is if I make both of them negative. And negative times a negative is still positive 9, right? So what are my two factors? X minus 3, x minus 3. I have 2 from my quadratic and 1 from each of my other factors. I can still condense this a bit further if I wanted, and I can call this x minus 1, right? And then x plus 1, and I have 2 of these. So x minus 3 squared, because I have 2 of the same term, right? These minus 3's repeat. That's why I write this one with an exponent. All right. So what's the overall idea here? We start with any power that we have, and our goal is to first find one factor. One factor. We do the rational root theorem to find the one factor. Then we're left with a cubic in this scenario, and our goal is, can I factor that cubic using the rational root theorem? If I can, I will repeat this process to find the other ones. If I can do it through grouping, then my goal is to split this up and to find the two groups, right? Now, depending on which one you found first, maybe you didn't go through this order. Maybe you would have. See how you have x minus 3 in here? That means that the minus 3 would have been part of the solution as well. So it all comes down to how you want to approach this, right? You can do this method here, the rational root theorem, multiple times to find multiple remainder zeros. And you can do all of the intercepts through here. You would have found 1, -1, and the 3 would have all worked. So you can just repeat this process over and over again, or you can go through this process where you find the cubic and then you break down the cubic, which gives you a quadratic, and then you break down the quadratic, and so on and so forth. Please let me know if you have any questions. Don't forget to like and subscribe. And as always, we'll calculate later.